We have already discussed that octahedral and tetrahedral. There are two types of complexes are there, coordination number 4 and coordination number 6. That is coordination number 6 forms octahedral complexes and coordination number 4 forms two types of complexes. One is tetrahedral, one is square planar. Now, in the octahedral field where the ligands approaches towards or along the axis, so we already know that dx square minus y square and dz square lobes are along the axis or on the axis, so same sign through 180 angle, it means it has geared, that is g, small g, that is the same energy, which indicates the same energy. So T2g and Eg. Now as the ligands in the octahedral field, we have already discussed that 6 ligands are there and 6 ligands approaches bond along the axis, so energy of Eg set will be higher, that is of feeling lower repulsion. T2g becomes more stable, having lower energy. Now in the tetrahedral geometry or entity, as the metal ion occupies at the central position of the crystal and 4 ligands are there, the ligands are approaching in between axes, so therefore the energy of T2 will be higher in case of tetrahedral geometry. We are going to discuss about different types of complexes with cobalt 3 ion. Now cobalt 3 ion having D6 system prefers low spin octahedral complex. Why they prefers low spin octahedral complexes? Because it gives maximum stabilization energy with CFC value, that is T2g6 Eg0, that means having value is equal to minus 24 dq with respect to barycenter. Highest CFC value, cobalt 3 plus ion prefers low spin high octahedral complex due to it gains maximum stabilization energy with minus 24 dq, that is with respect to barycenter, energy of barycenter. Now we already know that stability order according to CFSE value, square planar geometry or entity having highest CFSE value, whereas tetrahedral having lowest CFSE value. Okay, again zinc 2 plus ion forms complexes with ammonia. That means Zn NH3 plus prefers tetrahedral geometry. Why? Because zinc 2 plus ion is D10 system. Now in D10 system, our coordination number of here actually Zn NH3 whole 4 and then with 4 ammonia molecules forms tetrahedral complex geometry here, because in tetrahedral geometry the bond angle becomes 109 degree 28 minutes. That means bond angles are far apart from each other, having lower or lowest minimum repulsion value and greater stability. But in square planar geometry, we already know that square planar geometry the bond angle is 90 degrees, so the ligands are more closer than tetrahedral geometry. As in the tetrahedral geometry, the ligands are apart from each other far distance, and the distance here great decreases, so lone pair or ligand repulsion minimizes at the tetrahedral geometry, so it prefers tetrahedral geometry. Now artist's wheel, we already know that if any compound absorbs energy with higher wavelength, it emits energy or radiation with lower wavelength. That means it absorbs yellow color, it appears blue. It absorbs green color, it appears purple. If it absorbs red color radiation, it appears bluish green. Now color of every compound or complexes is due to two factors. We have already discussed in the previous classes that DD transition, that means D to D, that means T2 to EG, T2G to EG, EG to T2G, that means two sets between two DD transitions. If DD transition occurs for a particular complexes, we have a colored complex. Again, another factor is charge transfer transition, which generally occurs in the ions, where charge transfer from particular ion to metal. Now, so if there is no d orbitals or having all the d electrons are paired or filled, there is no d detention, so we get colorless complexes. Okay, now we are going to discuss about various types of application of coordination chemistry. Application, already we know that in our hemoglobin, in the blood cells, there is a central metal atom, that is iron. Again, in vitamin B12, that is cobalamin, contains cobalt. In applications with ammonium thiocyanate, that is NH4SN, forming complexes with normal FeCl3 salt, for forming a particular complex with blood color, red color, red color. That means if a knife with containing FeCl3 ion, and when it reacts with ammonium thiocyanate, it forms red color. This type of complex FeSN whole 2 plus. These type of complexes having blood colored, okay, just like real blood. Now, in the chemistry of boiler, that means for softening of hard water contains particular metal ion, that is calcium 2 plus, magnesium 2 plus. This type of ions, metal ions, can be removed by using ethylene diamine tetraacetic acid, flexidentate ligand. We have already discussed previous classes that hard water contains sub ion, that is calcium 2 plus and magnesium plus, with forms stable complexes with EDTA. Forming this complex with precipitation and gets removed, we get soft water. Okay, to get soft water we have to mixed hard water with EDTA. Now, in gold plating we use potassium orocyanate, and silver plating we use potassium argentocyanate. We have already discussed in our previous classes. Now, in the boiler chemistry industry, hot water having pot containing pots, there is a thick layer due to hard water in the utensils containing hot water. Sometimes it explodes, but if we use EDTA, the layer gets absorbed in EDTA, forming a precipitation and get removed from that utensils or boiler. Okay, and it gets cleaned. Again, in the formation of black and white photo, we use negative film negative, which can be produced by sodium thiocyanate solution in the AgBr, mixed with AgBr, and in the process named fixing, we forms a stable complex, that is Na3AgS2O3 whole 2, and this is the negative we used in the black and white photography. Okay. In the cancer treatment, we use cisplatin medicine. Cisplatin, that is the formation cis isomer of platin, that is PtCl2 NH3 whole 2, that is of cis isomer. It is an anti-tumor agent. Okay. Also, again, in our body, if lead, mercury and cadmium enters in some cases, we use EDTA, because EDTA reacts with these type of compounds and forms a precipitation, and it gets removed through urine. If these types of metal, heavy metals, poisonous metals enters into a human body, it can be removed by using EDTA. Okay. Now, an important scenario or an important topics is metal carbonyls. Very, very important. Why? Metals from carbonyl compounds. Here carbonyl used as a ligand, that is carbon monoxide used as a ligand. A particular type of bond happens to be here. Now, iron forming bonding. Iron forms bond with cobalt. Two types of bond are there. One is sigma and two is pi. How it occurs? First, carbonyl carbon, that is carbon monoxide having oxygen, donates it electron pair through carbon atom. Carbon monoxide carbonyl group donates its electron pair through carbon atom to the vacant d orbital of metal, forming sigma bond. So the first bond forms between them is sigma. Carbon monoxide with carbon atom donates its electron pair to the vacant d orbital of metal, and in this way it forms a sigma bond. Again, this sigma bond, when it occurs, it increases the electron density over the metal, and this high density of electron on the metal ion creates or helps the metal to form a pi bond by donating its electron from its a particular d orbital to carbonyl group to its pi star anti-bonding orbital. Actually, when sigma bond forms, metal becomes highly electron dense. This metal ion, when it is high electron density, having high density value of electrons, becomes much more higher density, and these higher density electrons, one electron pair from a d orbital of metal ion gets back donated to the pi star anti-bonding orbital of CO, forming pi bond. So the first bond is sigma bond and the second one is pi bond. This back bonding or back donation of metal to carbonyl via pi bond is known as synergic effect. This synergic effect, when sigma bond first time and then second time, it back donated by metal to again carbonyl group. Okay, this effect is known as back bonding or back donation or synergic effect. Okay.